A passive LC bandpass filter has a center frequency of 1 MHz. The LC network consists of a 33K ohm resistor, a 300 microhenry inductor, and a capacitor. Characterize the filter. To characterize the filter, we need to find the following: the cutoff voltage levels, the cutoff frequencies, bandwidth, Q, and the shape factor. But in order to find these characteristics of the filter, we need to find first the capacitor. So a bandpass filter that is a LC network is similar to the bandpass filter that we built in Lab 3, which is this one. We have a resistor and a tank circuit. So we know the value of the inductor, the resistor. Now we need to find C. In order to do that, we're going to use this formula. This is valid for an LC network, where the frequency is equal to 1/2 times pi times the square root of LC. Okay, so here we have the frequency, we have the inductor, so we can find and see. This is the formula. So I'm gonna use latex to write the formulas. So let's work. Let's solve for C, and here the quickest way is to take the square raised to the 2 power, the frequency, and also what's on the right of the equal sign, all this. Okay, so let's do that. We're going to raise frequency square and the fraction, which is going to be left. This is the way we enclose with parentheses. I need to raise this square. So if we square both sides, on the left we're gonna be left with frequency square, and on the right will be 2 square times pi square times LC. Okay, so here we're gonna get rid of the fraction, of the parentheses, here and here, and we will have 4 pi square. Okay, now square root, there is no square root, it gets cancelled. So this is what we have left. Now here, if we multiply by C both sides of the equation, we're going to end up here with the frequency square times C. C will cancel on this side, and also we can divide frequency square both sides, and we'll end up with frequency at the bottom. So let's do that. Basically we're swapping C by frequency square, and here with the capacitor. So this is the formula that we're going to use. The capacitor will be equal to 1/4 times pi square times L times center frequency square. Okay, and we're going to use Python as a calculator. First, we need to import, how is this? From math, import pi. Okay, and the center frequency, we know that is equal to 1 megahertz, e to the 6. Now the inductor is equal to 300 microhenry, which is e to the negative 6. What else do we have? That's it. That's what we have. Now, the capacitor is going to be equal to 1 over, all this in parentheses, 4 times pi square. And we're going to use the power function to square pi. So it's going to be pi raised to the 2 power times the inductor, which is L, times frequency square. We're going to use the power function again. Frequency raised to the 2 power. That's it. That's our formula. And that's equal to, oh, one more thing. We need to show this. So we're going to print the result of C. And comes out to 84.4 picofarads. 8.44 e negative 11, but if we adjust this into engineering notation, it will approximate to 84.4 picofarads. So we have 84.4 picofarads. Now that we have the value of our capacitor, then we can work on the schematic. So we need a